So set your function equal to 8. And again, you got that x squared plus y squared love. If I solve it for that, you bring the negative over here to the left to make it positive like this, at the cost of bringing 8 to the right by subtraction. So by the time you're at this equals 8 height, you get another circle with radius 1. So can you kind of see what this surface might look like? But all these circles are concentric and they're equally spaced, but are the z changes in altitude equally spaced?
No.
So if it were a cone,
5 and 3
would equal spacing of the circles also correspond to equal spacing of the z's? Yes, it should. A cone's growth is linear.
This is a,
okay.
there should be a bowl.
So this is more bowl shaped. And is it a bowl that's
Or
opening up like
sphere.
this, or is it capped up like that?
It's capped like that.
Yeah. Here's the xy plane, circle of radius 3. 5 clicks higher, circle of radius 2. Then at 8, 3 clicks higher, circle of radius 1. So your circles are getting narrower, and not in a linear direction, but kind of, steep at first and then sort of tapers off. Can I use z equals 9 here?
0.
Yeah, what do you get if you have x squared plus y squared equals 0? Point.
Yeah.
Yeah, it's not really a circle. If you want to, think of it as a circle of radius 0. So if I actually do plug in z equals 9, I get, really just the origin. So 0 to 5 clicks, 1 concentric circle in, and then 5 to 8 clicks, just 3 clicks higher, 1 other unit in for the radius. So fat, skinnier, skinnier, and then 1 click higher from 8 to 9, you got a point.
Could be going down, is it up?
So it is opening down. It is a bowl-shaped object opening down. It's properly called a paraboloid.
So level curves is like 2-dimensional elevation.
I'm sorry?
It's like a 2-dimensional view, a 3-dimensional
Yeah,
elevation.
this is just a 2-dimensional. I'm using the words topographic projection. Have you heard that before?
Yeah,
topographic map. So this is essentially showing you the change in elevation. So you can see a height of 0, 5, and then 8. You're going uphill as you go through these concentric circles. Okay.
So you can probably see that change a little bit better if your height intervals were constant.
Yes. Now, that's kind of hard to do freehand, which is why I want to introduce you to, I'm not sure if Beth has ever brought this up in class, there's a really handy software graphing package that I like to use once in a while that does that. It probably is out there for free somewhere on some kind of download website. I don't know because I don't do that thing. But no, it's called NewCalc. Has she ever brought this up in class before?
Sure.
So it's kind of handy to see. If I wanted to look at this surface, z equals 9 minus x squared plus y squared. Okay. So it'll graph in 3D, really fast. Let me change the resolution on it so it's not as picky. Okay, so, and change its shade so you can actually see what it looks like. Put a little gray frost on it. Zoom out a little bit. Okay. So the reason you're getting these little bat wing effects down here at the bottom is because this is graphing in 3-dimensional rectangular coordinates. And if you see this little thing right here, it represents your window domain. The x values exist from -4 to 4 in the x-axis direction. The y values are -4 to 4, and the z values in this window are from -4 to 4. Okay? No? Yeah, -4 to 4. So apparently we're seeing more z's than we actually should, because that should have a z-axis intercept of 9. That's kind of peculiar that it actually shows me this. But that's the reason you're seeing that sort of square cut, is because it's cutting it with x equals -4 to 4 and y equals -4 to 4. And to orient yourself, you see this is an axis and this is an axis, and the z-axis will be coming up through like this. This one to your left is your positive x-axis. This is your positive y-axis. Okay. So if I were to look at the level curves for this particular surface, the software does do that for us. We can change our view, we can go to the graph, and instead of viewing the surface plot, we can view a contour plot. And so this does represent equal spacing of z values. And let me change the gray here doesn't show up as well as something like blue or red. Okay. This does represent equally spaced z values. So over here, where you have a relatively close connection of the level curves, and then the closer you get to the middle, they get further and further apart. What does this tell you about the surface when the level curves are really close together?
Yeah.
Steeper. Yeah, because if this represents equally sliced distances in z, like maybe every 0.1 or every 0.5 or something like that, then whenever they're close like this, you got the same change in elevation here than you do here. So this will be easier to walk across because it's not as big a change in elevation than right there for that same tiny little distance. So the closer your level curves are together, the steeper the part of the graph is. Okay. Now, one thing that this is deficit on, first off, the scale is off kilter. Does that look circular or elliptical to you?
It looks
Elliptical.
Yeah, your aspect ratio is loopy. So, X. Anyway, it should be concentric circles because when we saw the equations that you get for each level curve is x squared plus y squared equals 1, 9, 4, something like that. So they should look more circular than this. But yeah, it's kind of a handy thing to pull up in a Calc 3 class once in a while so you can sort of see some of these multivariable functions that you work with, okay? One of the ones I'm going to lead into tonight, our first topic together, beginning of Test 3's material. And if you missed this, I've got a calendar for you. You're going to want to pick one of those up. The first thing I want to discuss with you is a topic that's in your textbook, section 14.5. It's the gradient vector, using the gradient vector and dealing with the directional derivatives. Have you talked about the gradient vector as of yet? Okay, so that is a brand new topic. So this is the first thing that I'll be working with you on. And again, between now and test time, your test again will be in the testing center. Can anybody have a problem using the testing center?
It's until next Monday, right?
It's until next Monday. Everybody's going to be able to use the testing center. Okay. So if you have any questions about the test, or feel free to obviously bring them up on Thursday night. I'll be getting here at 5:30. I'll get here 45 minutes early if you can get here that early. Go over any kind of extra questions that you got, and we can use a few minutes in class for not really review, but last minute Q&A. But just send me an email if you have any questions. Hopefully you wrote my email down. If you didn't, I can get it for you again at the end of class. But I'll put it on our D2L page eventually, all my contact information. So going into section 14.5. Oh, and one other thing I use the D2L page a lot more extensively than Beth will. When I finish the class notes tonight, I use the document camera all the time just like she does, but I actually take these notes, the new stuff, I will date them March 24th, and this is section 14.5 on gradient directional derivatives. So in the future, if you miss a class, you can go there and see what's missed. And Danielle's already set the standard for uploading the class video to her YouTube channel, so that's still available on your D2L page, I believe. So you can still access those as needed. But picking up where we need to be, 14.5. And again, shout out to me when you can't see what I'm writing. I need to adjust the camera. Gradient and directional derivatives. Okay. First off, I'm just going to show you how to calculate the gradient. I'm going to go into what the gradient is, but I want to get the rudiments of the calculation down pat because it's a really good partial derivative review. You still need partial derivatives. The gradient is a vector. Created using partial derivatives of a multivariable function. Okay. Most often it's going to be a two-variable multivariable function, a function of x and y. You can talk about the gradient of a function of x, y, and z, but the rule is, for as many variables as you have here, for as many input or independent variables you have, that dictates how many components you have to your gradient. So a function of two variables, I have an ij two-component gradient. A function of three variables, I have an ijk three-component gradient. And so heaven forbid a function of four variables, an ijk whatever that fourth dimensional, directional vector is. But yeah, the number of variables dictates what your gradient looks like. So for instance, just a quick for example, okay? that's the symbol for gradient. Use an upside down delta, which actually turns out to be something you see later in some differential equations classes called the del operator. It is a partial derivative operator. It essentially tells you to do something involving partial derivatives to whatever it's paired with. So the way gradient is defined for a function of two variables is this. It is a vector, so that means it has two components. I tend to use the brace notation for vectors with the funky little V-shaped brackets more than the IJK. So a function of two variables would have two components for its gradient vector. The first component is this, the partial of f with respect to x. The second component is the partial of f with respect to y. So that's kind of the definition of how you get the gradient for a function of two variables. Okay? I want us to find the gradient for this function. Okay, find the gradient for the function f of xy equals xy e to the negative x squared minus y squared. Okay, so for your next test, for test 2, you would simply be asked to find, what's the partial of f with respect to x, or what's the partial of f with respect to y. So building on that, we're going to use these as components of this vector. And I promise, I will tell you what this vector stands for, but I just want to go through as kind of like a quick partial derivative review to show you how to do the gradient. So the two things we need are right there. We need the partial of f with respect to x, and we need the partial of f with respect to y. So, partial of f with respect to x is going to start with this and leave who constant?
Y.
Y is treated as a constant, which means as a coefficient constant sometimes, or in some cases an additive or subtracted constant. Keep in mind the rule of a constant when you get to those particular parts of the derivative rules. So x is going to be the variable I focus my derivative attention on. So how many functions of x are involved here, and how are they related? Two. You have a product. You have x, y, x variable, y constant, and then you have exponential use of x. So I do need the product rule here, okay? If you want to split this that way, xy times the exponential, that's a good way to view this as a potential product rule layout. So I need this prime left alone plus this left alone times that prime. The product rule, okay? F prime g plus f g prime. So the derivative of this, the partial derivative of this with respect to x would give me x goes to 1, and what happens to the y?
Stays constant.
Stays constant, like a coefficient. So the derivative of this with respect to x would give me y times the exponential left alone. And then plus, you switch it up. If you leave this alone, xy is going to be left alone now, times the derivative of my exponential. And that's going to require sort of a partial derivative version of the chain rule. The exponential derivative is done first, so that outer part gives me what? The derivative for exponential base e.
2x minus
E to the same thing, yes. Yeah, so e's derivative is going to give you the same thing back. And then times, here's where I need the chain rule. The inner derivative here with respect to x is going to make me multiply by how much?
Negative 2x.
Negative 2x. The negative x squared becomes negative 2x. The negative y squared is an additive constant that goes away. So yeah, my chain rule multiplier puts a negative 2x here. So let me see if I can neaten this up. Well, I'll do that when I build the gradient, but that's the full-on calculation for getting partial with respect to x. Switch gears, start with a fresh copy of your function and do the first partial with respect to y. So now the xy, its partial with y gives me x times the e left alone, and then plus the xy factor left alone times the exponential derivative. So again, the exponential is going to be its own derivative again, times the derivative in that exponent with respect to y. So now the x squared annihilates, and the negative y squared becomes the negative 2y. So notice there's kind of a symmetry going on here. Because this function, it sort of produces this for the partial with x, and then when I switch from x to y, that switches, and that switches. That's kind of the same thing. Almost the same thing, not exactly. So because these are my ingredients for the gradient, I put those together. And again, the gradient of f of x, y, denoted with this del f symbol, is a two-component vector that has this as its I component. So one thing I'm going to do to make that a little bit neater is this. Since that exponential appears in both terms, I'm going to factor it out. And then what's left over from this would be y minus 2x squared y. And that's my full I component for the gradient. Doing the same factoring here, I can pull the exponential out. My partial with y becomes the second component for the gradient. So if I factor out that e, that's going to leave me with x minus 2xy squared. And then close off my V shape for the end of that gradient vector. Okay. So that's how to calculate a gradient. For any number of variables, how many variables you got, the number of variables in the parent function tells you how many components you've got. So just to kind of extend it, just to go one dimension higher. If I have w is a function of x, y, and z, and we'll make it a little bit easier. Let's say it's x squared plus y squared plus z squared. Okay. The gradient here would have how many components?
3.
Yeah, because you're always going to have to take a partial derivative with respect to each variable that's in the parent function. So that'll be a 3-component vector in this case. So here, I'll need the partial of w with respect to x. And it's always in alphabetical order. IJK is always going to be x, y, z partial derivative order every single time. It never switches up to where this is partial with z and this is partial with y, or it's always x, y, z order. So my middle component's partial with w with y. My k component is the partial of w with respect to z. So a little bit easier in this case because you've got 3 additive terms and they're going to have unique derivatives with x, y, and z one at a time. Partial with x is just 2x. The partial with y, positive 2y. Partial with respect to z is 2z. That's it. So the gradient's always going to be a vector quantity. Vectors have a direction and a magnitude, and I'll tell you what the direction and the magnitude for the gradient is unique to. But that's going to help by looking at the level curves of this surface. Okay? So let me switch out. I kind of wish we had 2 projectors in this classroom. So I could keep one on the document camera and one for the computer. So let's look at the graph of this critter. Z equals, and again, this is for the original function up here. Oh, hello, I've already spaced out. So Z equals xy times e raised to the negative x squared minus y squared. Okay, and let me do this in gray because sometimes with that black background, a frost color is always best to look at. So this function, oops, there's a little curves. Spoiler alert, spoiler alert. Let me do the surface plot instead. So you can kind of see a little bit of light effect on there. Actually, that's kind of lame. That's a little bit flat. I can zoom in a little bit, but I'll tell you what, let me use a stretch factor. Just like you can stretch a function by, the amplitude of a sine wave, let me put, say, the number 4 right there. It won't change the gradients effect. It'll just, make the function a little bit steeper, easier to see. There you go. So you got some more hills and valleys to look at. So again, the orientation on the software, that green axis right there is always your positive z-axis. You only see the positive z-axis. The software doesn't graph the negative z. Okay? You have a positive x this way, positive y that way. So that's the same right-handed system that you kind of been used to since the first part of the semester. And unfortunately, it's always the reverse of what you see in your E&S or your physics classes. I think in those classes, isn't the y-axis the vertical one?
Yeah.
And then x and z are down here. So sorry about the screwed up frame of reference. But here it's the same as in your textbook, the same as what you've been used to this class. Positive x here, positive y there, positive z up. So this is kind of a hill valley looking function. Got some waves to it and stuff like that. The further you zoom out, there's not too much extra activity. The further you go away from the origin, it kind of flattens out. You really only get those zits showing up right there toward the center. If you don't let me call them zits, they're kind of like bumps, pimples, whatever they are. But why is it that the further you go away, the flatter it gets? What attribute of the function's equation causes it to kind of flatten out like this?
Exponential growth.
The e to the negative exponent. Whenever you have e raised to something negative and large, and notice as you go away from the origin, the expression here, x squared plus y squared, gets bigger, but they're both negative. So that's essentially a large negative exponent you're plugging into e for these larger values away from the origin like that. So it causes your e to sort of make the function's height diminish. And it pretty much looks like the graph of the xy plane. I mean, heck, you see the software having trouble distinguishing the fact that this surface is actually supposed to be above the xy plane in some cases. It looks like it's sort of corresponding to it. But should look roughly like this. What I want us to do is to give you an idea of what the gradient looks like. Let me go to the contour plot for this surface. Okay, those 4 bumps that we saw there toward the center are represented by these level curves. And again, the software tries its best to use equally spaced z values as it slices through to produce this topographic kind of map, these projections. Can y'all see that pretty well when you switch colors? Okay, if you notice, sometimes it's light gray, sometimes it's dark gray. I think it's trying its best to put a little bit of shading for the elevation. So this is most likely a hilltop because it's a little bit lighter in color. This is also a hilltop, and these are likely to be valleys, okay? But without seeing some numbers for like, this is z equals 0.4 and this is z equals negative 0.4 or something like that, you don't really know. That's one of the purposes the gradient can help us out with. When you overlap the gradient function or the gradient vector with the level curves of a function like this, something really cool happens. The gradient's vectors kind of become a steepness compass. In other words, if you're standing at a point like this, and you had a compass that represented your gradient vector that we just found, it will be pointing uphill at any point on the surface. If I'm standing right here, it will be pointing uphill in that direction. Standing right here, pointing uphill. It always points in the steepest climb from wherever you are. So, it may take us a second to do it. I may need to use copy and paste to do it too. But I want to show you what the gradient vectors look like. So let me copy this expression, because it shows up in both of them. I need to produce the gradient by using a 2-component vector. So it looks a little bit like a matrix. Some of you may be taking matrix algebra this semester. That first value represents my I component for the gradient. This represents the J component for the gradient. So I want to type in those 2 expressions that we got. So if you double check on your paper, make sure I type this in here the right way. I factored out the E expression, and then inside the parentheses, I have y minus 2x squared y. So I'm going to actually do it this way. Put the square there last. There we go. And then for the J component for the gradient, there's the E that I factored out. And then in parentheses, I had x minus 2xy squared. So sorry about the screwed up alphabetical order here, but that should be the same thing, okay? So when I plot this will overlap with those level curves that vanish. Whenever you start doing some editing up here, it takes away the image. But when I hit enter, it'll put a series of vectors. They actually look like Q-tips. They look like little, oh heck, let me show you what they look like. Shut up and hit enter. Okay, let me zoom in a little bit. So you see the level curves that we had up there to begin with. That represents those valleys and peaks that we saw on the surface earlier. And you see all these, well, honestly, little purple Q-tips all over the place. But you only have one piece of cotton swab on these Q-tips, so they're kind of like the Q-tips you have at the doctor's office. And notice, some of these vectors are a little bit longer than others. Some of these right here are a little bit longer than those that are closer toward the center. These are a little bit longer, these are a little bit shorter. Each of these purple vectors are individual representations of the gradient, or they're all gradient vectors. What the gradient tells you is the arrow points in the steepest uphill ascent from where you are. So if we were standing at this point on this surface, then the steepest climb that I'd make to go uphill would be in that direction, okay? If I went left or right of where I am, I'm not going any steeper. I'm going in a more shallow slope. Okay? Or actually, if I walk on the level curve, my elevation is not changing. I'm just sort of staying at the same Z height. But if you go in that direction, and this is where you really need to see this as a square ratio. Can I stand in your seat for a second?
Yeah.
Can you pause? I'm gonna try to get this thing fixed. And I don't think my shoes are dirty, so hopefully I won't get your answer. You sit back down. So pardon me. Alright. I may need to, let's see. I don't want to get help, I just want to get the
Hit the
menu.
arrow buttons to make your screen go either left or right.
Well, so that'll fix the positioning. No, that's the volume. I need volume. I just need the menu. There we go, menu. I want, let's see. It should be image. Color, brightness, contrast, sharpness.
Signal.
Settings.
Maybe just reset.
Don't
Don't reset?
turn it upside down.
Oh, for real? She's done this before.
No, did it
Okay.
matrix.
What'd you say?
Yeah, it is
We did it
upside,
matrix.
Oh,
it's
you did the
upside down
matrix,
right now,
Yeah.
so it needs to be.
So it needs to be this
Yeah.
orientation. It needs to
Input.
be upside down. I just want aspect ratio.
Yeah, right there.
Where?
Third from the bottom.
Oh, third from the bottom. There we go. Maybe normal.
16 by 9.
Yes. Okay, now.
If you do 16 by 9, it might give us, well, never mind.
Twist it to the left.
Oh,
That's the
16:9?
computer screen anyway.
No love.
No, they got
Right,
square
I was
screen up
thinking,
there.
yeah,
Yeah.
Or native.
because it's not, it's the square screen
Yeah.
on the computer.
Position.
Is it not just swivel?
Okay. Oh no, I'm backwards.
It's twisted.
But what about?
No, that's not- okay, so now you just need to
it's
turn it.
Actually,
Just turn the
just turn the
box
whole
itself.
housing.
Yeah.
oh gosh, I'm gonna break it. That's good enough. That's
Yeah.
good enough. You can see everything. Is that too
Probably
tiny for you?
thing that wouldn't break.
You
that's
do,
good.
you do the wood.
Oh yeah.
They attach those to the ceiling with some rigid pipe.
Go back.
Oh, see, that's what I'm saying.
There's a physical zoom.
The physical zoom on that little
Oh.
indentation there. Forward by the
Forward.
lens.
By the lens. By the lens.
Up, up.
Up. Oh, there you go.
There you go.
Okay, so now
Up until the left.
Now you just grab it and move it.
just need to.
Manhandle
It's
it.
not really exactly on a ball swivel here. Kind of locked. Y'all don't need to see the menu from the bottom. I think that might work. Okay, so menu. Good deal. So you need to be able to see this in proportion, so that way you can actually see the scale of vectors. There's one very, very important thing about the way these vectors meet the level curves. Each one of these gradient vectors intersect these level curves in a very special way. Can you eyeball? Yes. To each one of these level curves, the gradient vectors are perpendicular to that particular level curve itself. So when you draw a gradient tailed on a level curve, here's one that's pretty close to being tailed right there. That purple vector is perpendicular to that direction of the level curve at that point. And does that kind of make sense? If you're going to try to ascend in the steepest way possible, let's say I'm standing right here and that point is looking in the steepest way possible uphill, you'd need to go perpendicular to that level curve of elevation that you're standing on to go to the next level of elevation up. You want to try to seek the closest distance between the two consecutive level curves. And that would require you to leave the level curve you're on perpendicularly to get to the next level curve.
Is it always in the direction of R prime?
It's always in the direction of uphill. This is not R. This is a function of two variables. An R function is technically just a curve in space. So these aren't graphs of surfaces. These are just graphs of things like lines or curves or helixes. So you can talk about them being a path, but you can't talk about really, standing on it really. Okay, it's just really a path. So the only thing you can really measure here is its length. Here, if you're standing on a surface, you can measure the surface area. So we're a little bit one-dimensional higher. We're still in 3D. That's in 3D. This is in 3D. But we're standing on a surface as opposed to a curve. So this is always going to be perpendicular to the level curve itself, the concentric circles like we graphed earlier. Okay. So that's one of the handy things about the gradient is the gradient's always going to be perpendicular to your level curves. And they're always going to point uphill. So if you look at these four images, these four different humps, can you tell now which ones represent hilltops and which ones represent valleys?
See.
See, is that Spanish yes?
Yeah.
Okay.
Because it points
I was
from
like,
the
there's no
outside.
multiple choice here.
The
Let's
outside
see.
in.
So,
We.
all right. Yeah, the arrows are the little round tips at the end of the purple vector. So pointing uphill here means this is one of the peaks. This is one of the hilltops. All these are concentrically kind of pointing here, so that's also a hilltop. So whenever you're in a valley or a recess, your gradient vectors are pointing away from where you're standing. Okay, so because if I'm in a valley, uphill is going to be away from the center of the valley. Okay, what happens to your gradient vector if you're at the peak or in the center of the valley?
0.
Okay, it goes to 0. This goes over to something that the partial derivatives measure. Remember, this is a gradient vector that's made up of the partial with respect to x as one component, the partial with respect to y as the second component. If I'm on a function of two variables, and I love to draw, so let me draw a picture. If I'm on this particular surface, and let's say we're at one of the peak points right here, okay? And this is the increasing x direction, and this is the increasing y direction. So the partial derivative with respect to x slices into this kind of vertically and measures the rate of change, on this hill going in that direction, okay? So if you're standing at the peak point right there, that's one place where you'd have a horizontal tangent line. So whenever you're at a peak, your partial with respect to x measures a slope of 0. It evaluates as a 0 partial derivative slope value. Same thing with your partial with respect to y. If you were crossing that in the increasing y direction, okay, your derivative there in the y's partial derivative direction would also be 0. So when both of them go to 0, that means you have to be at a peak point like this, or possibly in a valley recess like that, okay? You could be, your partial with respect to x would wipe out one way, and your partial with respect to y would also wipe out to a 0 value. So, since they both represent the two components in this gradient, let me show you something kind of cool about this software. I can grab one of these Q-tips. Well, I can grab the origin and shift it around like this, but I can actually grab one of these Q-tips and kind of move it around. Like if I pick this one up, notice it actually picks up a copy of it. Okay, and then the closer I get to the center, the closer I get to in this case, the hilltop, you see what's happening to my components of that vector.
Shrinking.
It's shrinking. Look over here to your left. Up here in the upper left corner, and I'm pointing to it as though you can see my finger, but you see x and then a coordinate and y and a coordinate. That represents your location on the xy plane. But then you see x component and y component. That represents the components of the vector for gradient itself. So if you look at the magnitude, the absolute value of these components, the further I get away, the higher they get, the longer they get. But the closer I get to the center, my x component, my y component, they're getting smaller in magnitude because they represent the partial derivatives with x and y. And when I finally get to that, as close to the center as I can, right there, sometimes you can get lucky and get a 0, sometimes you can get it to go to scientific notation for a really darn small number. But the closest I can eyeball where the peak would be somewhere right about there, okay? And that's relatively small component values for the gradient vector. I can't exactly get to the 0, 0 sweep mark, but it's pretty close to it. It's got to be somewhere in that location.
Okay? You could zoom in really far.
Yeah, I could just keep doing that until the components would eventually let me hone in on a little bit closer. But so a couple of important things about the gradient. The gradient points uphill